Okay, in the last class, we have started series and parallel combinations of capacitor as well as resistor. Waalaikum Abdullah. So now we will be doing circuits of capacitor and resistor simultaneously. Resistors are given in chapter number 3, but we'll be doing both capacitor as well as resistor simultaneously. So the first one is series and parallel combination of capacitors. But before starting series and parallel combination, you should know how charge and voltage divide. To decide whether a given capacitor is in series or in parallel, you should know how charge or voltage divide in two different capacitors. And the theory that we will develop for capacitor will be valid also for resistors by some minor changes. So we'll be doing them side by side. Both capacitor and resistor will do side by side. So first I'm starting with division of charge. Division of charge and potential. Or you can say division of voltage. So this division of charge and voltage are not directly given in NCERT, but to decide whether given capacitors or resistors are connected in series or they are connected in parallel, you should know this division. On the basis of these divisions, you can decide whether a given system is in series or in parallel. So let's first start with division of charge. Division of charge. So charge divides due to branching. If there is some branching in your system, then the charge will divide. If there is no branching, then charge will not divide. So you can say charge divides due to branching. Charge divide due to branching. Now, let's see what do you mean by branching? What does branching exactly means? Say you have a wire, a straight wire. This is a straight wire. Some charge Q is passing through the wire. There is no branching in the wire, so charge will remain same. Same charge will flow through the wire. There is no division of charge. Even here, there is no branching. The wire is just folding. There is no branching in the wire, so charge will remain same. Charge here and charge here will remain same. So charge will divide only due to branching. When you have branching in your system, then your charge will divide. Like this one. This is here. So this is charge Q. When charge Q entered this branch, it divided into two parts. It's Q1 as well as Q2. The charge gets divided into parts, Q1 and Q2. So charge divides due to branching. Whenever you have branching in your system, your charge gets divided. I'm giving you a few capacitors. Can you tell me whether the charge will divide or not? You have two capacitors, one capacitor C1 and another capacitor C2. Yes, what do you think? The charge will divide or not in these two capacitors?
No, it will not divide.
Yes, sir.
It will not. There's no branching here. But if I extend this system like this,
Yes, sir, it will divide.
Charge will divide.
can you decide which two capacitors will have same charge?
C1, C2?
C1, C2. If some charge enters here, then the same charge will reach to this capacitor also. So these two will have same charge, but now the charge will divide into two parts. One is Q3, another is Q4. Right? So just by looking at the circuit, you can decide whether your charge divides or not. If you have branching in your system, then charge will divide. Or the division of charge and division of current is same. Charge or division of current is the same. You can say charge or you can say current. The only difference is you will consider charge for a circuit having capacitor only. But instead of capacitor, if I give you resistor type circuit, like if I give you this circuit, two resistors, then in resistors charge flows. That means you will have current. So there is no branching, so same current will pass through both the resistors. But if you have branching, then current will divide. This is I1, this is I2, and this is I3. So current divides due to branching and charge divides due to branching. The difference is in circuit of capacitor, we will consider charge, but in the circuit of resistor, we will be considering current. Note it down and tell me if you have any issue.
Sure.
Okay, I'm changing the slide. Huh? Fatma, I just have started. You can take screenshot. That's the first slide.
Yes, sir.
Taken?
Yes, sir.
That's the second. Okay. After this division of charge, the next is division of potential. Division of potential. See, potential divides due to discontinuity offered by resistor or capacitor. If you have resistors or capacitors in your circuit, then potential will change, potential will divide. It divides due to this or capacitor or resistor. I'm giving you one example. Say if you have a straight wire. Just 1 second. Let me connect my charger. Just 1 second. Yeah, sorry. So if you have a straight wire, we already studied in electric potential that surface of a wire is equipotential surface. Amalia, what do you mean by equipotential surface? Amalia, what do you mean by equipotential surface? Okay. Mariam, do you remember what is an equipotential surface?
Yes, sir. The potential at any point of the wire is equal.
The surface which have same potential at every point. So if I take a conductor, a conducting wire, surface of conductor is equipotential. That means if I take point A, I take point B, I take point C, all points will have same potential. VA is equal to VB is equal to VC. But if in this straight wire, you have resistors and capacitors, then potential will change. At one end of the capacitor, potential will be something else. On the other end, it will change. Like if I connect a capacitor to this wire, now potential will change. Over this end, let's say the potential is VA. Then over this end, potential will change, that is V. And we don't use potential in the circuit, we use potential difference. So we use potential difference across capacitor. Potential difference across capacitor. So across capacitor, potential difference is VA minus V. So this is the potential difference across the terminals of the capacitor, that is VA minus V. That's the potential. Similarly, if instead of this capacitor, I take a resistor. At point A, potential is some VA. And since you have a resistor, then potential will change. Here potential is VB. So potential difference, and we also call potential difference as voltage, V is VA minus V. So if you have a straight wire, potential will remain same at every point, but due to resistor and capacitor, the potential will change. I'm giving you one example. I have two capacitors. I just have to decide whether these two capacitors have same charge or same potential difference. If charge is coming through this wire, will both capacitors have same charge? Fatima, will both the capacitors have same charge? Fatima is not answering. Mariam, will both the capacitors have same charge?
No, sir.
Charge will divide, right?
Yes, sir, because
Charge.
it is bracket.
Charge will divide into two parts. One part have charge Q1, another part will have charge Q. Yes, the charge will divide into two parts. One is Q1, another is Q2. Now let's check whether they have same potential difference or not. Let's say I give this point a potential V. So Ahmed, will this point have same potential V or potential will change?
It will have same VA.
Same potential, because these 2 points are connected through a wire, conducting wire. Conducting wire have same potential V. Sania, can I have potential VA over here also?
Yes, sir.
Yes, sir. If I have a capacitor, then potential at both the ends is same or it's different?
It will be VA and VB.
So if this is VA at one end of the capacitor, the second end will have same potential.
No, it will be VB.
See, it's not necessary that you always write VB, it's your choice. You can write VC, VD, V alpha, whatever you want. But the thing
It
is,
will be different.
it will change. Okay, now what about this point? Will this have same potential VB or something else?
It will have same.
You see, Sania, we decided through the wire. Just think from this point to this point, you have a conducting wire. Is there any
Yes.
breaks on the wire? No. Wire is
No.
not breaking from anywhere. Is there any resistor or capacitor in between 2 points? No, there is no resistor or capacitor. So both the points will have same potential.
Yes.
Padma, what is potential difference across C1? Padma, what is potential difference across C1? Padma, you can write in chat room if you want. I need potential difference across C1. Amalia. What is
So does VB not
it's
act if the capacitor?
VA minus VB. This is potential difference across C1. And what is potential difference across C2? V2, which is again VA. Yes, Fatma, you are correct. Minus. So this is the potential difference of voltage drop across the capacitor C1 and C2. So Ahmed, what do you think? These two voltages are same or different?
So they are same.
They are same. V1 is equal.
So
So these two capacitors have different charge, but they have same voltage. Yes, Ahmed, you're asking something?
so what if the capacitor have different value?
No issues. Even if your capacitor have different values and these 2 points are connected by a conducting wire, directly by a conducting wire, there is no breaks here. Then these 2 points will have same potential. This result is independent of the capacity. You can have capacitance of any values. If they are connected by a straight wire, then potential will be same. Okay, Ahmed?
Yes, sir.
Okay. So the motive of doing this topic is to decide just by looking at the circuit that capacitors or resistors have same charge or they have same potential difference. So you can remember, if capacitors are connected end to end, then they will have same potential difference. If there is no branching, then they will have same charge. I'm giving you few examples. Like I'm giving you this example. You have these two resistors. One resistor R1, another resistor R2. Will these two capacitors have same current or different current?
Same current.
Same current.
Same current.
There is no branching, so they will have same current. So I1, I2, same current. Sorry. Do they have same potential difference?
No.
No.
They're not connected end to end. They will have different potential. Okay, if I take this example, these are two resistors. One have resistance R1, another have resistance R2. Some current I is flowing through it. Current will remain same or it will divide?
It will divide.
Current will divide because you have branching. Your current will divide into two parts. This is I1 and this is I2. What about the voltage?
Remains same.
Voltage will remain same because both are connected end to end connection. So if here voltage is V1, here is also its V. Voltage will remain same. So just by looking at the circuit, you have to decide whether your given capacitor or resistors have same current or same voltage. If they have same current or same charge, then they are in series. If they have same voltage, then they are in parallel. This is how we decide series and parallel combination. Okay, just note it down. Then we will start series and parallel combination of capacitors. Now you know how we do division of charge and voltage. Amalia, is it clear? Tell me once you have written.
Done, sir.
Done, sir.
So the last slide, 1 second. Just it.
So done.
Yeah.
Can I change it, Fatma?
Yes. So
That's it.
Sure. Okay. The next is series and parallel combination of capacitors. Series and parallel. Combination of capacitor and resistor. So we will be doing resistor and capacitor simultaneously. First, we will do series combination. So along with resistor, a major part of chapter number 3 will be finished. Because in chapter 3, you have series and parallel combination of resistors. So on the left hand side, we have capacitors. And on the right hand side, we have resistors. So and series combination of both capacitor as well as resistor. So series combination means there is no branching. When I say capacitors are connected in series, that means there is no branching. Charge stored in each capacitor is same. So series combination means in series combination, charge stored in each capacitor is same while voltage divides. Similarly, when I write for resistor, I will write in series, the same statement. In series combination, instead of charge, we have current. And current is not stored, current flow. Current through each resistor is same while voltage divides. So that series combination, charge is same while voltage divide, and in resistors, current is same while voltage divide. So we have various capacitors, they are connected in series. It's C1, it's C2, it's Cn. So you have n capacitors and all capacitors are connected in series. Similarly, here, you have n resistors and they all are connected in series. It's R1, it's R2, it's R. So it's connected to a cell. The voltage of the cell is V. Similarly, I connect to a cell, the voltage of the cells. See the difference between both the circuits. In this circuit, current flows. Means charge is in motion. Current is just flow of charge. There is no branching, so same current will flow through all resistors. But when we do circuits of capacitor, charge does not flow here. Charge gets stored in each capacitor. Each capacitor, this battery or cell gives some Q amount of charge. That Q amount of charge gets stored in each capacitor. Each capacitor have stored same amount of charge. Now this charge is not flowing. This is stored in the capacitor. So that's the difference between the circuits of capacitor and the circuits of resistor. In resistor, charge stored in each capacitor is same. In resistor, current passing through each resistor is same. The next is the motive of doing this series and parallel combination is using the series combination of capacitor. You want to remove all capacitors. You want to use a single capacitor which produce the same effect that is produce all these capacitors together. Like the effect that all C1, C2, Cn are producing, the same effect will be produced by a single capacitor. That capacitor is known as equivalent capacitor. We are supposed to calculate the equivalent capacitance of the circuit, C. And we connected it to a cell of voltage. Similarly here, you're supposed to calculate the equivalent resistance. And we connect it to the cell of voltage. Now, in the next step, see the total potential difference across the circuit is equal to voltage of the battery. You can say that total potential difference is equal to V. Means across this whole circuit, across the complete circuit, the total potential difference is V. And this potential difference gets divided. V1, here it's V2, here it's V3, Vn. Similarly here, this voltage of the battery gets divided into n parts, V1, V2, Vn. This voltage divides in a way that stored charge remains same. Here voltage divides in a way that current remains same. Now, for the next 5 minutes, I will concentrate only on capacitor. Then we will discuss resistor separately. Just tell me if you have any doubt till this point. Dullah, Ahmad, Fatma, Noor.
No, sir.
No, sir.
So the voltage across each capacitor is V1, V2, and Vn. The voltage across the system is V. So you can write V as, it gets divided into n parts. It's V1 plus V2 up to Vn. The total charge provided by stored in the circuit is Q. If total charge is Q, then each and every capacitor will have same charge. See, there is a relation between voltage and charge. You can write that voltage is Q by C. If you have charge and you have capacitance, you can type voltage. See, the total charge stored in this capacitor is Q. The total capacity is C equivalent. Can you write V in terms of Q and C equivalent, Fatma? The total charge stored in this capacitor is Q. The total capacitance is C equivalent. Can you write V in terms of Q and C equivalent, Fatma? Mariam?
Yes, sir. Q by C equivalent.
Q by C equivalent is V. Good. Q by C equivalent. Fatma? In this circuit, can you write V1 in terms of Q? Fatma, write V1 in terms of Q. Fatma, you're not audible. I can't hear you. You can write in chat room. Can you write V1 in terms of Q? Write a formula for V1 in terms of Q. Sania, what is V1? How will you calculate V1 in terms of Q?
V1 by
I need V1.
1 by Q.
Yes.
Q by
This is voltage charged by capacity. So V1 is Q by C. Sania, what is V2? in this circuit. The charge stored in this capacitor is Q. Capacitor. How much?
Q by C2.
Q by C2. Similarly, Vn you can write Q by Cn. And this is Q by C1 only.
But the first one will be Q by C1, right?
Yeah, C1. Then you can see Q gets cancelled out from both the sides. And you are left with 1 by C equivalent is 1 by C1 plus 1 by C2 up to 1 by Cn. This is how we calculate equivalent capacitance if capacitors are connected in series. Okay, if I repeat the same thing for resistor, like if I repeating the same type of calculations for resistors, then in case of resistor also, the total potential difference is V. This voltage V of the cell gets divided into n parts, V1, V2, Vn. You can write this V as V1 plus V2 plus Vn. Okay, Abdullah, just 1 minute. We will tell Fatma, can you write this? See, this is the voltage V and the current through the equivalent resistance is I. And in resistor, we use Ohm's law to calculate voltage. V is equal to I. So here this V is I into R equivalent. V1 is I into R1. V2 is I into R2. Vn is I into R. So this I gets cancelled out. So I'm left with only R equivalent is R1 plus R2 plus Rn. This is how we calculate R equivalent. R1 plus R2 plus R. So if your capacitors are connected in series, then we calculate 1 by C equivalent as 1 by C1 plus 1 by C2 up to 1 by Cn, and equivalent resistance as R1 plus R2 plus R. Okay, so it's Salah time. So I'm just giving 5 minutes, 7 minutes, Greg. I'll start after 7 minutes.
Thank you, sir.
Yes, Abdullah. Noor, shall I start? Yes, shall I start? Abdullah, Noor, Fatma, shall I start?
Yes, sir.
Okay. So this is how we calculate equivalent resistance if your resistors are connected in series. You should remember both things simultaneously. We are doing simultaneously not just to save time, but due to the fact that when you get a question on DC circuits, the same question that can be made using a capacitor or a resistor. So you can remember these relations simultaneously, then it would be easier for you to solve. Next. Okay, Mariam, which quantity will remain same in all the resistors? Charge will remain same or current will remain same?
Sir,
In capacitor. Charge will
charge.
remain same or voltage will remain? Charge will.
Charge.
You can say that same charge.
यार अहमद गर्मी है यार अंदर की चल रही है भी है ना ऐसे आप दफा हो जा पंखा बंद कर दे निकल
Same charge stored in each capacitor. Each capacitor. So you can say charge stored in first capacitor is equal to charge stored in second capacitor, which is equal to charge stored in nth capacitor, that you can write as C equivalent multiplied by. This is how we calculate charge stored in each capacitor. Q1, Q2, Q1, which is equal to C equivalent multiplied by the voltage. But if you need voltage, see, voltage across each capacitor is different. For the first capacitor, voltage is Q by V. For the second capacitor, voltage is Q by C2. Nth capacitor, voltage is Q by Cn. And what is Q? Q is total charge. Here you can write total charge. What is the total charge stored in capacitor? Total charge is Q. Total charge is total capacity multiplied by V. In capacitor, we write Q is equal to CV. So total charge means total capacitance and total voltage. So that is C into V. Here total current I is total current I is V by RE. That's total current I is V by RE. The same charge stored in each capacitor Q1, Q2, Q1 is equal to C equivalent to V. Now, if you need voltage across each capacitor, potential difference across each capacitor. Then voltage across first capacitor is V1, which is equal to Q by C1. For second capacitor, it's V2, which is Q by C2. For nth capacitor, it's Vn, which is Q by C. So this is the voltage across each capacitor, Q by C1, Q by C2, Q by C. After voltage across each capacitor, the next thing is energy stored in each capacitor. Sania, do you remember any relation for calculating energy stored in capacitor? Sania, expression for energy stored in capacitor. No. See, to calculate energy stored in each capacitor, you can use this expression Q square by C. For first capacitor, it will be half Q square total charge divided by C1. Similarly, you can write energy stored in second capacitor as half it's Q square by C2. Similarly, you can write energy stored in nth capacitor. It's half it's Q square divided by C. This is energy stored in each capacitor. For total energy stored, you can do two things. You can either add them up, energy stored in each capacitor, or you can write this as half Q square by equivalent capacity, C equal. So this is about capacitor. See, if you have a capacitor, then capacitors are connected in series. Then you remove all capacitors, connected a single capacitor C equivalent. Total charge stored in C equivalent is C equivalent multiplied by V naught. Total voltage across the circuit is V only. This total capacitance C equivalent can be written as 1 by C equivalent is 1 by C1 plus 1 by C2 up to 1 by Cn. Then you can calculate charge stored in each capacitor. In series combination, charge stored in each capacitor is same, that you can write Q1, Q2, Q1, which is C equivalent into V. Then you can calculate potential difference across each capacitor, which is different. V1 is Q by C1, V2 is Q by Cn. Then you can calculate energy stored in each capacitor and total energy. These are the parts of the numericals. Like in a numerical, you may be asked about equivalent capacitance, charge, voltage, and energy stored. Now, next what we can do is, let's start the resistor. R equivalent is R1 plus R2 plus R. Then we will calculate current through each resistor. Current through each resistor. Current through each resistor is same. So the total current which is coming out of the cell is flowing through all resistors. You can say current flowing through each resistor is same, which is equal to the total current in the cell. So you can write this as I1 is equal to I2, which is equal to IN, which is V by R. Then you need voltage across each resistor. Voltage across each resistor. So Ahmed, if I know current and resistance, can I calculate voltage V1? Ahmed.
Yes, sir.
The resistor, the current through R1 is I, resistance is R1. What is the voltage V1?
Voltage is different. V1, V2, and Vn.
No, I'm asking a expression of voltage in terms of current. The
In
current flowing through this resistor is I, resistance is R1. Can you write V in terms of I and R1?
Yes, sir.
What that expression would be?
V equal to IR.
So V1 will be IR1.
1.
Similarly, we can write V2 as
IR2.
IR2. You can write Vn as IRN. So this is how we calculate voltage across each resistor. After voltage, next what we can do is power dissipated across each resistor. power dissipated across e-joules. Power means energies dissipated across e-joules. So that power can be calculated as P is I square R. So I'll be using I square R1. P2 is I square R2. Pn is I square R. Next, we need total power dissipated. Total power dissipated. So you can write total power as the sum of all powers, P1 plus P2 up to P. Or for total power, you can write this as I square into RE. So that is about series combination of capacitors as well as resistors. Okay, note it down. Then we start circuits on series combination. Okay. So I'm changing the slider.
Okay, sir.
Fatma, is it clear this series combination of resistors and capacitors? Fatma, Amalia.
Yes, sir.
Amalia, you're not responding today. Okay. Sania, just log out once and then log in again. It may be due to internet issues. An internet issue. Just log out once and then log in again. Okay. Yes, can I change the slide now? Sania, is it visible now?
Yes, sir.
Okay, Sanya, please take screenshots. Huh? This is the first slide. You will use this formula in numericals.
Done, sir. Yes, sir, done. Done.
Can I change the slide now? Ahmed, Abdullah.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, let's start with some circuits. Huh? Can I change the slide now? Fatma, Mariam?
Yes, sir.
Yes, sir.
So first circuit, very simple circuit. You have two capacitors and these two capacitors are connected in series. This is a capacitor of, let's say, 5 microfarad. And this is capacitor of 10 microfarad. The voltage is 10 volt. See the simple formula based numerical. I'm not modifying anything. Calculate first part. I need equivalent capacitance, C equivalent. Second part. I need total voltage across the circuit. Voltage and potential difference is same. I need total voltage across the circuit. Next, I need total charge stored in circuit. Fourth part. Then we need charge stored in each capacitor. Charge stored in each. Fifth part. Voltage across each. Sixth part. Total voltage across, total charge stored in each, voltage across each, and then you need energy stored in each capacitor. Energy stored in each capacitor. And then in seventh part, I need total energy stored. Total energy stored. And I'm removing this micro here, just keep it as farad only. So you have 5 farad and 10 farad. Okay, start your calculator. It's a formula-based thing. All formulas are written in these slides. This is for the equivalent capacitance. This is for the total. This is for the total potential difference. This is the total charge. Then you have formula for charge stored in each, voltage across each. Then you have energy stored in each, total energy stored. The formula-based question. Calculate it and write your answer in chat. Yes, Ahmed, first part is correct. Noor, also first part is correct. What about the rest? The first, just keep on calculating. Calculate one part and then write that in chat. Don't answer all parts together. Let's keep on answering one part at one time. Yes, Noor, second is correct. Third is correct, basically. Yes, third part. Yes, the second part. Yes, it's correct. Yes, Noor, second is correct. No, Sania. Sania, is it first part?
Yes, sir.
What is P?
Sir, by mistake.
Hmm?
It was by mistake.
It was?
By mistake.
Acha. You're writing just 3.
It was 0.3.
0.3. Good. Right. Yes, Fatma, your first part is correct. Noor, your third part is also correct. Ahmad, second is wrong. Amalia, first is wrong. Amalia, it's just 5 farad and 10 farad. Just 5 and 10. No micro, nothing. Amalia, use this relation as a simple relation. 1 by C1 plus 1 by C2 is 1 by C equivalent. That's it. Calculate it again and then report your answer in chat room. No, Abdullah, you can calculate total charge directly. No? You can calculate total charge in this way. C equivalent multiplied by B. This is your, how can calculate total charge?
Yes, sir.
Yes, no, your fourth part is also correct. Good. Fatma, Mariam. Yes, Fatma, first part is correct.
So charge will be CV, right? C equivalent into
C
V.
equivalent will be total charge, right? Yes.
So 10 by 3 will be C equivalent and 10 is the potential difference.
C equivalent is 10 by 3, yes. And then multiplied by
10.
10. So that will be 100 by 3.
Yes, sir.
And what you have written 100 by 3. So you are calculating. But for the second part, I need total voltage. You are calculating total charge.
No. Total charge stored.
Okay. That's the third part of the question.
Okay, yes. Yes, sir. Okay, yeah.
That's why I was saying. Okay, Mariam. No, Fatma, see, total voltage is this always. Total voltage is the voltage of the battery. That's it. Total voltage is always the voltage of the battery. Yes, Noor, you're right. So total voltage is 10 volt only. The answer of part 2 is 10 volt. What about the rest? Okay, Fatma, is it clear? The total voltage is the voltage of the battery only.
Yes, sir, clear.
Sania, second part is 10 volts. Try calculating the third part, total charge. This is the total charge. C equivalent into V. Good, Sania. All three are correct. Now calculate the fourth one. Amalia, you're making mistakes. See, 5 and 10, you are taking parallel combination of 5 and 10. Your second part is correct, but your first is wrong, Amalia. Okay, Fatma, third is also correct. Okay, I'm solving it. First part. Okay, just stop your calculations for a few minutes and see. 1 by C equivalent is 1 by C1 plus 1 by C2. So 1 by C equivalent is 1 by C1, which is 1 by 5, 1 by C2, which is 1 by 10. Now you can take 10 as LCM, so it's 2 plus 1. So your 1 by C equivalent is 3 by 10, but you don't need 1 by C equivalent, you need C equivalent. So your C equivalent will be 10 by 3, which you can say 3.3 farad. That's C. Few of you were writing it as 3 by 10 only as 0.3. It's not 0.3. You have to take reciprocal. Second part. Next, we need total voltage across the circuit. The total voltage across the circuit is always the voltage of the cell. It's 10 volt. Third part. You need total charge stored. See, this is the formula for total charge stored. Total charge stored is total capacitance multiplied by the total voltage. C equivalent into V. So total charge is C equivalent multiplied by. So you can say total charge is C equivalent, which is 3 by 3, multiplied by V, which is 10. So Q is 33 Q. So this is the total charge stored, which is 33 coulomb. I'm just taking your answer, Abdullah. Just give me 2 minutes. Huh? That's the total charge. Next, we need charge stored in each capacitor. So see, for charge stored in each, you know that charge stored in each capacitor is equal to the total charge. If you look at this circuit, charge stored in each capacitor is equal to the total charge stored in the circuit. So for part 4, Q1 will be equal to Q2. And this is equal to the total charge stored, that is equal to 33 coulomb. Is it clear? The first 4?
Yes, sir.
Amalia, is it clear the first part? Okay. See the next 5th part, voltage across each capacitor. So to calculate voltage across each capacitor, we'll be using this relation. See, total charge divided by capacity, charge stored in capacitor divided by capacity. So I can write V1 as total charge divided by C1. So what is the total charge? Total charge is this. Total charge is this 33. Divided by C1. What is C1? C1 is 5. That is C1. No? And this is C2. So that's 33 by 5. Good. Similarly, I can write V2. V2 is Q by C2. It's 33 by 10. So this is how we can calculate voltage across each capacitor. V1 is Q by C1, 33 by 5. V2 is Q by C2, 33 by 10. 6. Next, we need voltage across each capacitor. After voltage across each capacitor, we need energy stored in each capacitor. So energy stored in first capacitor is half Q square divided by C1. So this is half. Q is 33 square. C1 is 5, this much of U. I'm not calculating it now. Similarly, you can calculate U2 half Q square divided by C2. So it's half. Q is 33 square. C2 is 10. Next, you need total energy. For total energy, just add them. Just add them the individual energies and we'll get total. Is it clear, everyone? All parts?
Yes,
sir.
sir.
See, it's a very, very straightforward circuit. You will get complicated circuit, but in all complicated circuit, the maximum data that you can calculate is this. In a circuit, the maximum quantities that can be calculated are these quantities, 7 quantities. Just note it down, then we'll repeat the same circuit with resistor. And you will see the calculations are very much similar. There's just some minor differences in the formula. Just note it down and tell me once you have written this slide. Yes, can I change the slide?
Yes, sir. You will not get these type of circuits in exam. Please.
See, next question. You have two resistors. No issues, madam. So this is 5 ohm, this is 10 ohm, and this is 10. See, the question is similar. Calculate first part. R equivalent, second. Total voltage, sorry. Total current, 4. Current in each resistor, voltage across each, 6th. Power dissipated across each, yes, Sania, this is correct. Last, total power. Yes, do it now. The calculations are comparatively easy than capacitor. You have all relations. Yes, Ahmed, first part is correct. Sania, second part is also correct. Ahmed, second part is correct. Yes, Noor, first is correct. Fatma, Mariam, no, sorry, Mariam is not. Fatma, Amalia, passed. Yes, Noor, first and second both are correct. Sania, first, no, third part. Ahmed, yes, Ahmed, you are right, correct. Noor, third is also correct, good. Fatma, you're not calculating? No, Sania. Sania, this is the formula for current. See, this is the formula for total current. This V by R equal. Current is voltage by resistance, and you are multiplying. Fourth is yes, Noor. Fourth is also correct. Good. Abdullah. Ahmed, check your calculations. I think you're making some mistake in current. The total current is same, so individual current will also be same, na? I1, I2 is equal to total current. Yes, Fatma, first is correct. Abdullah, first two are correct. Samia, Sania. Yes, Sania, now you are correct. Okay, Abdullah, third and fourth both are right. Correct, right. Yes, Fatma, second is also correct. Amalia, first two are correct, third is wrong. See, current is not voltage into resistance. Current is voltage divided by resistance. Third is wrong, and I think fourth is also wrong. Huh? No. Fourth is correct, but third is wrong. See, total current is total voltage by total resistance, Amalia. Third part is wrong. Fifth part, Abdullah, voltage across each. Yes. Just a second. Current is. Yes, Abdullah, both are correct. Yes, Ahmed. Sixth. Yes. V1 is correct. Okay, Abdullah, power is also. I think power is correct, like I square R. Let me check your power, Abdullah. This is I'm calculating the power. Noor, fifth is right. Okay. Good. So now you people know these basic circuits. Yes, Fatma, third is correct. So the first part, you're supposed to calculate R equivalent. R equivalent is simply R1 plus R2. So R1 is 5, R2 is 10, R1 plus R2 is 15. Total voltage is 10 volt. Total current I is total voltage by total resistance. Total voltage is 10, resistance is 15. So your current is 2 by 3. Current is 2 by 3. Similarly, part 4. Current in each. So the current that flows through the cell also passes through the resistor. So current through each resistor is same as that of total current. So I1, I2 is equal to I, which is 2 by 3 ampere. Fifth part. Voltage across each. Voltage across each capacitor is same. Like V1 is I1 R1. I1 is 2 by 3. R1 is 5. So it's 10 by 3 volt. Similarly, it's V2. I2 R2. 2 by 3 into 10, it's 20 by 3 volt. 6, power dissipated across each. Power dissipated is comparatively easy. Power dissipated is I1 square R1. So what is the current flowing through the first capacitor, first resistor? I1 is this 2 by 3. So this is 2 by 3 square into R1, which is 5. So it's 20 by 9 watt. Yes, Abdullah, you are right. P2, it's I2 square R2. So I2 is same, 2 by 3, R2 is 10, so it's 40 by 9 watt. If you want total power dissipated, then simply add them up. So it's 20 by 9 plus 40 by 9, it's 60 by 9. Yes, Emil. 60 by 9 watt. This is the total power dissipated. Is it clear?
Yes, sir.
These
Yes,
two
sir.
numericals was just for the sake of use of formula. Now you know how to use different formulas. Now, just like we did series combination, we will first develop theory of parallel combination simultaneously for capacitor as well as resistor. Then we will see circuits having combinations of series and parallel. Okay, just tell me once you have written. Amalia, is it clear every step? Just note it down and tell me once you all have written.
Done, sir.
Done. Okay.
So done.
Now, parallel combination. Next is parallel combination of both capacitor as well as resistor. You should always remember the basic difference, one of the basic difference in capacitor and resistor. In capacitor, charge stored. We use capacitor to store charge, while in a resistor, current flows. So we have few capacitors connected in parallel. So this is one capacitor C1. This is another capacitor C2. You have another capacitor Cn. All these capacitors are connected to a cell. The voltage of the cell is V. This is how all these capacitors are connected to the cell, voltage of the cells. See, in parallel combination, if you can check, all capacitors are connected end to end. All three capacitors are connected end to end. That means they all have same voltage. They all have same voltage. What about charge? Can you decide charge? Is charge through each capacitor is same or charge will divide?
It will divide.
It will divide.
There is branching in the circuit, so charge will divide. If charge Q travel from the cell, it will divide into three parts. Some Q1 gets stored in C1, Q2 gets stored in C2, Qn gets stored in Cn. But voltage across each capacitor is same. So you can write in parallel combination, voltage across each capacitor is same while charge divides. Now, instead of capacitor, if I take resistor, I take few resistors, one, R1, I take another resistor, R2, I take another resistor, Rn. I connected them with a cell of voltage V. What do you think? Current through each resistor will be same or current will divide?
It will divide.
Divide.
There is branching, so current will divide. Current will divide. So you have current I. You will have I1 here. You will have I2 here. You will have In. So in parallel combination, voltage is same. I'm writing in short form. Voltage is same, but current divides. You should remember one more thing for numericals. Here, charge is proportional to capacity. So the capacitor having a higher capacity will have more charge, but your current is inversely proportional to resistance. So resistor having higher resistance will have smaller value of current and pass through. Okay, after this, the next point is we will remove all capacitors, we will remove all resistors and replace it by a single capacitor or a single resistor. Charge stored, resistors. The next is equivalent capacitor. I remove all capacitors, replace all capacitors by a single capacitor. This will produce the same effect as produced by the individual capacitors. I can remove all resistors and can use a single resistor. It will produce the same effect. This is V. This is the total current, total charge through the cell, total charge stored in the capacitor, total current flow. Now, I think now you can decide many things. What is the total potential difference?
It's V.
Total potential difference is always equal to the voltage of the cell. That's V. What about the total charge?
Q.
Total charge. How do you calculate total charge?
So Q1
V
plus
equal
Q2.
by into V.
Can I write total charge as total capacity into voltage?
Yes, sir.
Yes.
In the
Yes,
same
sir.
way, what is total potential difference here?
V.
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 What about the total current? Yes. What is the total current I?
IV.
V by R equivalent.
V by R.
It's total voltage by total resistance. Okay, next. Now, if I want voltage across each capacitor, Will it be different or same as that of the voltage of the cell?
Same.
Same. So next, if I want voltage across each capacitor, then voltage across each capacitor V1, V2, Vn is equal to V, equal to the voltage. Similarly here, if I need voltage across each capacitor, sorry, not capacitor, a resistor, it's the same, equal to the voltage of the cell. V1, V2, Vn is equal to the voltage of the cell. Next is to calculate charge stored. Charge stored in each capacitor. Charge stored in each capacitor. See, you have a capacitance C1, you have voltage V, and what will be the value of Q1?
C1V,
Similarly, what is Q2?
C2V,
C2.
C and V. Q1 is equal to C1V. Okay, we'll do it later. We'll first calculate C equal. Here charge divides. So can I write Q as Q1 plus Q2 plus Q1?
yes,
Charge is
Yes,
divided. The total charge provided by the cell get divided into n parts. So I write Q as Q1 plus Q2 plus Q. Q I can write as Q is equal to CV. I can write this as C equivalent into V. Q1 I can write as CV in V. Q2 I can write as C2V. Q1 I can write as C and V. So this V, this V, this V, this V gets cancelled. And we get C equivalent is C1 plus C2 plus Cn. Now, can you guess in the circuit of resistor, instead of charge, which quantity we will use?
correct.
Current we will use. Huh? The current will divide into n parts. I1, I2, In. What is the formula of total current? This is total current, V by R equal. What is I1?
Current first.
V by R equivalent.
Yeah, not R equivalent. R equivalent is total current. I'm asking I1.
This is
V by R1.
V by R1.
Similarly, I2, V by R2, I3, V by R3. Or I should write this as N. 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 I1, V by R1. I2, V by R2. In, V by R. Let's get cancelled. 1 by R equivalent is 1 by R1, 1 by R2, 1 by R. R1 by R equivalent is 1 by R1 plus 1 by R2 plus 1. This is how we calculate R equivalent. After R equivalent, the next is, so we have equivalent capacitance, we have equivalent resistance. Now we know voltage across each capacitor. I need charge stored in each capacitor. Charge stored in each capacitor. Yes, what's the formula of Q1? We just have used
C1V,
C1V, right? Q2,
C2V,
C2V. Qn is CNV. Okay, instead of charge, which quantity we will calculate in resistor?
current.
Current we will calculate. Current through each resistor. First calculate I1. I is V by R. Then we will calculate I2. It's V by R. Then we calculate In, which is V by R. N. This is how we calculate current through each resistor. So we have charge, we have current, and we have voltage. The last is energy. We just need energy stored in each capacitor and then energy stored in each resistor. Energy stored in each capacitor. Energy stored in each capacitor. U1 is half C1 V1 square. U2 is half C2 V2 square. Or you can write UN as half Cn Vn square. If you need total energy, then you can do two things. For total energy, you can either add them up, you can either add them the individual energies, or you can write that your total energy is half C equivalent into V square. Total capacity, total voltage square. Instead of energy, what term we will use in resistor?
Power dissipated.
Power dissipated. Power dissipated in each resistor. So a good portion of chapter number 3 is complete in each resistor. So P1 is half V square by R1, V1 square by R1. P2 you can write not V square by R1. This you can write V2 square by R2. Then you can write Vn square by Rn. For total power, keep them adding. P1, P2, P. Add them. P is V square by R equivalent. This is how we can calculate total power. Start writing. Then we'll do numericals on parallel of resistor as well as capacitor. Then we'll do mix combinations. Tell me once you have written to change the slide.
Done, sir.
So done.
They're done.
Done, sir.
So done. said one.
Done, sir.
Can I erase it?
Yes, sir.
Yes, Fatma. Can I change the slide, Sania?
Yes, sir.
Sania.
Yes, sir.
Said
Okay. Amalia, just tell me once you have written. Huh? You noted this slide? No, again. We'll do two numericals, one on capacitor, one on resistor. So one is 5 farad. Ten farad. Are connected to the cell of 10. See, I need calculate. First, I need C equivalent. Second, next I need total voltage. Third, I need total charge. Fourth, I need charge voltage across each. Voltage across each. Fourth, I need charge stored in each. Charge stored in each. Sixth, I need energy stored in each. Last, I need total energy stored. I need energy stored in each, and the last one, I need total energy stored. Start your calculation. This is easier than the previous one. Yes, first is correct, Ahmed. Okay. First, second, both are correct. Sania, you have to add them up. Why are you getting 3? This is the formula of equivalent resistance capacitance. Na? C1 plus C2. Yes, Ahmed, third is also correct. Yes, Noor, first is correct. Yes, now. Yes, Sania. Now, Fatma. No, Fatma, see, for C, these are connected in parallel. For parallel combination of capacitor, it's C1 plus C2, not 1 by C1 plus 1 by C2. Yes, Noor. Yes, second is correct, third is also correct. Yes, Ahmed, this is also right. Abdullah. Fatma. Okay. Okay. Yes, Noor, fourth is also correct. Very good. Okay, Ahmed. Yes, first and second both are correct. Good. Yes, Noor, both are correct. Yes, Sania, second is right. Third, Sania, charges C into V. This is total charge, Sania. C. C equivalent into V. Yes, what's the answer of third part, Fatma? Second is right. Second is correct. Yes, now you are right. Sania, yes, you are right. Amalia, your answers? Yes, Fatma, third is correct. Ahmed, okay. Yes, Ahmed, it's right. Yes, Noor, both. Yes, sixth is correct. Yes, Fatma, fourth is also correct. Yes, Noor, seventh is correct. Amalia, first is correct, second is correct, third is correct, fourth is also correct, fifth is also correct. Very good. Now calculate sixth and seventh bar. Yes, yes, Ahmed, you are correct. Oh, that means now you people understand how to solve these circuits. See the first part. C equivalent is C1 plus C2. It will be 5 plus 10, which is 15 farad. In the second part, I need total voltage. Total voltage is 10 volt. Fatma, that's Q2, I think. Yeah. So that's my C1 and that's my C. So I can write for the third part. I need voltages. Huh? So voltage across both the capacitors is same. No, next third I need total charge. Total charge Q is C equivalent multiplied by V. So now total charge Q is C equivalent, which is 15 multiplied by 10. So total charge is 150 coulomb. That's the third. Fourth part, we need voltage across each. So V1 is equal to V2, which is equal to. We need charge stored in each capacitor. So Q1 is C1 V1. C1 is 5, V1 is 10. So that's 50 coulomb. Similarly, Q2 is C2 V2. C2 is 10, V2 is 10. So that's 100. Sixth part. So we have voltage, we have charge. The sixth is energy. Energy is half for first capacitor, it's half C1 V1 square. So it's half into C1. C1 is 5, V1 is 10 square. So U1 is 100 into 2.5, 250. Similarly, you can calculate U2, which is half C2. I'm not calculating it, C2 V2 square. Seventh, you can write U is U1 plus 2. Yes, is it clear? All parts?
Yes, sir.
See, these are very simple circuits, but once you get used to of these circuits, you can handle complicated circuits very easily. How we make complicated circuit? We make complicated circuit by various combinations of series and parallel combination. Means in a complicated circuit, you can get this circuit 3 times. Or you can have the combination of this circuit and this circuit. this circuit. When NCERT says circuit is complicated, that simply means just combining both the concepts. So if you know how to solve this circuit and you know how to solve these types of circuits, then you can easily solve the complicated circuit. That's why I'm.
So what about bridge?
What about?
Bridge combination.
Yeah, bridge we will do. Bridge, you have infinite circuit. Those are some special type of circuit that we will do. But we can do those type of circuits only once these basic circuits are clear. So can I change the slide?
Yes, sir.
Yes, sir.
One last basic circuit. This is R1. This is R2. R1 is 5 ohm. R2 is 10 ohm. This is 10 ohm. Fast. Calculate first part. R equivalent, second part. Total voltage, third part. Total current, fourth part. Voltage across each, fifth part. Currents through each. No, Fatma, you are wrong. See, when resistors are connected in parallel, then we calculate R equivalent in this way. You have resistors now, not capacitors. Solve it. No need to calculate power dissipated. That's straightforward thing. Ten, Amalia. 10. Yes, Noor, you are correct. R2 is 10. Yes, Noor, second is correct. Ahmed, first two are correct. Yes, both are correct. First, second, third is. Sanya, first three are correct, but fourth is wrong. Check your answer of part 4. Ahmed, third is wrong. First is correct, second is correct, Abdullah. Yes, Ahmed, third is right.
So only 5 questions for this?
Sorry?
Only 5 questions for this?
Yes, only first part. For part 3, you're getting 3 ampere.
Yes, sir.
Okay. Let's solve. See for the first part. 1 by R equivalent is 1 by R1 plus 1 by R. So 1 by R equivalent is 1 by R1, which is 5, 1 by R2, which is 1 by 10. So that's 10, it's 2 plus 1, it's 3 by 10, or your R equivalent is 10 by 3. Second part. In second part, I need total voltage. Total voltage is 10 volt. Total voltage is 10 volt. After total voltage, the third part that you need is total current. Total current is total voltage by total resistance. Yes, 3 ohm only. Yes, Ahmed Abdullah, you were correct. That's 3 ampere. For the fourth part, we need voltage across each. So voltage across each is same. V1, V2 equal to 10 volt. Next, in the fifth part, I need current through it. So I1 is V1 by R1. V1 is 10, R1 is 5, so it's 2 ampere. I need I2, which is V2 by R2, which is 10 by 10, which is 1 ampere. Is it clear, all parts?
Yes, sir.
Yes, sir.
Okay, so these were basic circuits. Huh? Now you know how to solve circuits of capacitor and resistors. The next type of circuits that we will do will be combinations of these circuits. So the first circuit that we will be doing. Yes, can I change the slide?
Yes, sir.
Yes, sir.
Yes.
Next circuit that we will do is the next type of circuits are like this circuit. Let's do this circuit. So this is 10 microfarad. Say this is 5 microfarad. This is 10 microfarad. And this is 10. This is the circuit. So you're supposed to calculate C equivalent here. Then total charge or total voltage. Third, total charge. And fourth is total voltage, total charge, voltage across each, and fifth, charge stored in each. This is one solid example of NCR. This example is not given in capacitor, this is given in resistor. So from now onwards, I will solve circuit for capacitor and resistor will be your homework. And if I'm solving a circuit for a resistor, then for capacitor, that will be homework. You can get same circuit on capacitor or on resistor. So for my convenience, I am naming some circuit. I'm saying this circuit as A. Do one thing, name this circuit as A. We'll call this circuit as A. This circuit is A. The circuit having two capacitors or two resistors in series is circuit A40. I'm writing this name for my own convenience. I say that this is my circuit B and this is also my circuit. Now for this circuit, you have to identify circuit 1 and circuit 2 into it. Can you find circuit 2 into it, circuit B into it, into this circuit? You have to break this circuit in circuit A and circuit B. Can you find a circuit B here?
Sir,
Where?
5 and 10.
5 and 10.
These two are in parallel. This is circuit. This is circuit. So first solve this circuit B. See, when you have mixed combination, all capacitors are neither in series nor in parallel. You have to pick small parts of the circuit. So I picked this part. This is B part. So you know that C2 and C3 are in parallel. C2 and C3 are connected in parallel. So we can write this as C23 is C2. I'm naming the parallel combination of these two as C23, which is 5 plus 10, which is 15 microfarad. This is C23. Next, we will make a sub-circuit. Sub-circuit means I will remove these two capacitors, and instead of these two capacitors, I will add C23. This is C1, which is 10 microfarad. This is C12, which is 15 microfarad. And then you have a cell of 10. Yes, which circuit is this? This is circuit A or circuit B? This is circuit A.
A.
These two capacitors are connected in series. You know that in series we write 1 by C equivalent as 1 by C1 plus 1 by C12. So I can write 1 by C equivalent is 1 by C1, which is 10, 1 by C12, which is 15. So I write 1 by C equivalent as, you can take 15 as 150 as LCM. So it will be 25. So you will get 150 by 25, and it comes out to be 6 microfarad. Ahmed, it's not 1 by 6, it's 6. Yes, no, you are right. So C equivalent is 6 microfarad. Now, the next task is, you all know how to solve this circuit. This is the first circuit that we had solved. You know how to solve this circuit. Do one thing for me. For this circuit, get the value of total charge and total voltage. For this circuit, calculate how much is V1. Calculate how much is V1.
Sir,
Just a second. Q1
can
and yes, yes.
sir, can you take the previous slide?
Yeah, the previous one.
Sir, for this we can make it like 3 by 30 plus 2 by 15, 2 by 30, right?
Why 2 by 30?
LCM, like 30 as LCM.
This LCM of 10 and 15.
Yeah.
30. Yes. You can write 30.
And it will be like 5 by 30.
5 by
So
30.
it will be
1 by 6. But
say
that
this
1 by 6 is 1 by C equivalent, na?
Yeah.
Then you will take reciprocal of. Okay, I'm saying first note it down and then tell me how much is V1, how much is V12, how much is Q1, and how much is Q12.
Sure.
And also, hey, just a second. What is the total voltage and what is the total charge? Calculate. Yes, Abdullah.
It should be V23, right?
Oh, sorry. Yes, it's V2. Basically, I'm asking you to repeat the question, first question of capacity. Do it fast. Calculate total voltage, total charge, voltage across C1, voltage across, this is 2, 3. The name is 2, 3. 2, 3. Voltage across 2, 3. 2, 3. Do it now. You all know how to solve this circuit. That's why I was saying if the basic circuits are good, you can solve any circuit. Okay, Ahmed. Yes, you're right. Then get the value of total voltage. Fatma, Sania, what is the total voltage? Then total charge I need.
10 volt.
Yeah, total voltage is 10. Write it down. Then calculate total charge. It's total capacitance into total voltage. Take care of unit. It will not be coulomb. It will be micro coulomb. There is one micro everywhere. Don't ignore this micro. You will have micro everywhere. So it's micro coulomb. I won't leave the class until you complete this numerical. Yes, no. Second is 10. Right. Good. Sania, yes. Second part is correct. Total voltage is correct. Now calculate total charge also. Yes, no. Charge is also correct. Amalia, total voltage is correct. Amalia, I don't need total voltage. I need total charge. Na? Charge is CV. C equivalent into V. You are dividing. Amalia, you are not calculating a circuit of resistor. Na? You are solving circuit of capacitor. Okay, okay. Yes, Mariam, I'm sending the class. Okay, I'm solving it. I am just ending this class. C. Total C equivalent we know. Next we need total voltage. Total voltage is 10 volt. Next we need total charge. Total charge is always total capacity into voltage. What is total capacity? Total capacity is this 6. Total voltage is 10. So that's 60 microcoulomb. In the fourth part, I need voltage across each. See, let's solve this circuit. In this circuit, charge stored in both the capacitors would be same, right? They are connected in series. So Q1 and Q23 will be same. You can say that Q1, Q23 is equal to total charge, which is equal to 60 microcoulomb. From here, we can write V1. V1 is Q1 over C1. So that's 60 microcoulomb divided by C1, which is 10 microfarad. So I'm writing units, 60 microcoulomb, 10 microfarad. So you can see that 10 and 10 will get cancelled out. So it's 6 volt. Similarly, I can write V23. V23 means voltage across this capacitor. You know how to calculate V23. It's Q23 by C23. It's Q23 by C23. How much is Q23? 60 microcoulomb. How much is C23? 10 microfarad. If I cancel them, then this becomes actually. After V23, the next thing that we have is
Sir, C23 is 15, right? So it will be 4.
15.
Yeah.
Oh, yes, it's 15. Yes, yes, yes. Thank you. So it's 15. So it's 4. There is one small issue here. See, we know charge stored in Q23. We know charge stored voltage across V23. But V2, what is C23? C23 is basically a combination of two capacitors. We have to break this in terms of these capacitors. First, we calculated C23, charge stored in 2, charge C23, voltage across V23. Next, we have to divide this C23 into C2 and C3. What type of circuit is this? It's type A circuit or type B circuit?
Type B.
Type B circuit. How much is C2? C2 is 5 and C3 is 5. You have to keep on breaking these circuits in type 1 and type 2. It's type 2. And the total voltage across the circuit is this, V23. The total voltage is V23, which is 4 volt. They are connected in parallel, so they will have same voltage, V2, V3, which is equal to V23, which is equal to 4 volt. You can also calculate capacity, Q1 dot Q1. Charge, Q2 is C2, V2. You can calculate Q3, which is C3. This I leave for you. So if you know those basic circuits, you can solve any advanced circuit. Just keep on breaking your complicated circuit in terms of type A and type B circuits. Have you written this?
Yes, sir.
Oh, note it down. We have few more types of circuits left, but need some one more hour to complete this. Yes, Abdullah, class is over. Yes, everyone have written?
Yes, sir.
Yes, sir.
Okay, so let's stop here. We'll continue this in the next class. I need just
Thank you, sir.
one more hour to finish up this.
Thank you, sir.